The next problem on the page was actually another worksheet before, so I'm going to move on to page number 5. Okay, page number 5. The first question says, what is the angle between two of the phosphorus-chlorine bonds in a phosphorus tetrachloral ion? So PCl4+. So PCl4+, let's calculate the amount of valence electrons. We know each chlorine brings in 7, and that's 28. And we know that we have 5 from phosphorus because the periodic table tells us that. And we also know that the positive charge means we're going to subtract a valence electron because a positive charge means you lost an electron. So we're going to have 32 valence electrons. We start with phosphorus as the central atom. And I'm not going to draw in all the valence electrons on chlorines because you know that those are just going to be full octets on those chlorines. But we end up having all 32 valence electrons included now in our structure, which means this is the structure of PCl4 plus ion. Alright? And they want to know what the angle is. So in order to find out what the angle is, you have to know what kind of structure this is. And this is a tetrahedral structure. So tetrahedral structures always have the exact same bond angle. They have the bond angle of 109.5 degrees. And that is therefore the bond angle between the phosphorus-chlorine bonds. Alright, I'm going to erase the board and we're going to complete the next question on the page. Alright, this next question says, consider the carbonyl fluoride molecule, CF2O, and there are some questions about this molecule. Well, in order to do those questions, we have to draw out the molecule. So let's draw out the molecule. So we know carbon is going to be the central atom. We know we're going to have the oxygen attached to carbon. And we know that the two fluorines are going to be attached as well to the carbon. And we're going to fill in their octets. And that's 16. And then we have a bond between carbon and oxygen. And that's 18. And we realize we need a double bond between carbon and oxygen to make oxygen neutral. So there's a double bond. And now we just have to fill in the two lone pairs on oxygen. And we realize we have our full structure. We have all of the valence electrons that we need. And this is the structure of CF2O. Now we can answer the questions regarding the structure. The first question says, what is the central atom? Enter its chemical symbol. Obviously, you would enter the symbol C for carbon. How many lone pairs are around the central atom? Well, you can answer that question as well. How many lone pairs are there? There are 0. Carbon doesn't have any lone pairs in this equation, in this molecule. Now, we see what is the ideal angle between the carbon-fluorine bonds. So, when they talk about ideal angle, they mean the largest possible angle that you could have if they're pushing each other apart as far as possible. And the answer to that is 120 degrees. So the ideal angle is 120 degrees. But so far your answers have been carbon, 0, 120 degrees. And when they say compared to the ideal angle, you would expect the actual angle between the carbon-fluorine bonds to be, and the answer is you expect them to be less than 120 degrees. And you expect them to be less than 120 degrees because of the pull of the electrons. Alright, that's it for this question, and there's only one question remaining. I'm just going to erase this problem, and I will complete that last problem for you. Okay. Alright. The last problem says, answer the questions on the table below about the shape of the sulfur dioxide molecule. Okay, now instead of S2O, we have SO2. So SO2. Again, we do have the same amount of valence electrons though, because again, all 3 of them contribute 6 valence electrons for a total of 18 valence electrons. This one is much easier. We have sulfur in the center, and we have an oxygen on both sides. We know we have to have a double bond because otherwise each oxygen would be charged because it needs to be happy. In order for it to be happy, it needs a double bond and 2 lone pairs. So we will fill those in and see how many electrons we've used. If we count, we have 2, 4, 6, 8, 10, 12, 14, 16. And we know we need 2 more, so the 2 more have to appear on sulfur. Sulfur is one of those elements that can be an exception to the rule of carrying 8 electrons in its shell, so it is now carrying 10. Alright, and now we can answer these questions that they have about this structure. How many electron groups are around the central sulfur atom? And they even gave you a hint saying, note, 1 electron group means a lone pair, 1 single bond, 1 double bond, or 1 triple bond. So as you can see, there's 2 double bonds, so that's 2 groups, and a lone pair, so that's 3 groups. So the answer to the first part is 3 groups. And the answer to the second part, they say, what phrase best describes the arrangement of these electron groups around the central atom? So I'm only assuming that they mean the electron geometry, because they said the arrangement of electron groups, so that would mean electron geometry. So this is how the electrons are arranged. So if you wanted to see the electron geometry, you'd have to draw this a little differently. So you would draw it more realistically. The 1 pair would be pointing in that direction, and the 2 oxygen groups would be facing as far apart as they can possibly be, because the electrons repel each other, because they are like charges, so they repel one another. So, and they would be evenly dispersed. So each of these angles is all the same, and in this type of molecule, the angles are all 120 degrees, because this is a trigonal planar. Trigonal planar. And you can determine that based on looking at that chart that tells you if you have this many electron groups and you have this many lone pairs, then this is the name of your electron geometry. And the electron geometry is different from the molecular geometry because electron geometry is counting the electron pairs. So like here in this example we have a lone pair. Electron geometry accounts for that lone pair. Molecular geometry just tells you what it looks like what it physically looks like, not what actually makes it up. So the electron geometry tells you if there's a lone pair there, but you would say that this is a seesaw shape when we're talking about the molecular geometry, because the molecule, if you ignore everything else and just cover up that electron, that lone pair with your hands, all you see is a seesaw shape. So they call it a seesaw.